Okay, hi everyone. We're gonna go ahead and get started. Thank you guys so much for coming. Hope you've been having a good week. Today we're gonna be doing back to recursion again, but we're gonna be talking about fractals. So hopefully you've seen this already in lab. I think it's lab 8 or 9. I think it's lab 8. I think it's the one that was due today. So hopefully you've already gotten good practice with fractals, but I'm just gonna be going a little bit more in depth with it, or I guess not even more in depth, but just give you a better process for approaching them and kind of some guidelines to follow, because fractals are really important for understanding recursion, and they're also going to be important for your midterms, specifically your in-lab midterms. So we're going to just go a little bit more in depth with that. We're mainly just going to be doing like some examples. So feel free to like stop me at any time if you have questions about how we figured out how to do something, and we'll see how long this takes. You might finish early if we get through all the examples, but we can always do more at the end. So yeah, and let me start with announcements. So for announcements wise, homework 3 is due on Wednesday, next Wednesday, so a week from today. So come to homework party this Thursday or tomorrow to get some help with that, get started on that. I know it kind of seems like it's a little further away, but and it might be like after the midterm, so you might be tempted to like only start it after the midterm, but we really don't recommend you do that. I would say like work on it a little bit like this week, like maybe like tonight, tomorrow, like maybe a little Friday, and then you can like focus on the midterm and then start again like after the midterm. That's what I would recommend, but definitely come to homework party if you want to get some help on that. That's also going to be hybrid, so it's going to be in person and also online. Midterm is coming up on Monday. So this is going to be held from 6 to 8 p.m. A whole like logistics post went out last night. I think Vedansh posted it. So you should be able to see that, and just make sure you read all the way through it. It has all the information that you should need for like knowing how to take the midterm, where to take the midterm, when it is and stuff. But it's this Monday, 6 to 8. If you need any like adjustments, meaning you can't take it at that time, you can't take it at that location, you need to take it remotely or anything, make sure to fill out the adjustments form. So I think that's actually in a separate post on Ed, but they both were posted on Ed last night. So make sure you fill out that form by Thursday night. And I know that's kind of a quick turnaround. That's like tomorrow night. But make sure that you get that done, just because we need to figure out like details and logistics of how to make sure everyone gets the accommodations that they need. So yeah, if you have any issues or questions about that, please come up and talk to me after, or send an email to CS10 at Berkeley. And then the last thing about the midterm, so we're going to have a review session on Saturday morning from 10 to 12 in the morning. And it's going to be here in the same room. It's not like required or anything. It's just like a review session for you to like, like get you a little help with studying. It's going to be in person, and I think it's going to be recorded and then posted after. I think we'll try to do a Zoom live stream, but I'm not sure if it'll be like live stream, but it'll definitely be recorded and posted after so that you can watch it. But yeah, are there any questions about the review session? Yeah.
I can't find the form.
The adjustments form? Okay, let me see if I can pull it up and see exactly what the post is called.
Oh wait, I just reloaded it.
Okay. Do you know does it say or do you see the title of the post?
Maybe there's no adjustment form.
Okay.
There is?
Midterm logistics. Yeah, maybe on that one. Yeah, I know it's kind of confusing. I think a lot of posts went out last night. So the midterm logistics post has all like the logistics of the exam. And I think that has a link to the adjustments form. So that's if you need different times or different, like if you need it online. But there's the other one, which the other post is about the midterm review session. So this has information about where that's going to be held. And then also the midterm review session, it's going to be, there's like a survey, and that's what's the other survey that's linked. And that one, if over 20% of the class like fills it out, then everyone will get an extra credit point. And basically it's just like a survey asking what topics you want to be focused on the review session. So it's really for your own benefit. It's just for us to know like what you guys would like to have most covered, or like what you're the most shaky on, so we can kind of help you study for that. So yeah, that survey is on that post. So please fill it out as soon as possible so we can like get the right information and prepare our material for Saturday. Are there any questions about the midterm? Okay, and I didn't put this on here, but so the paper midterm is the one that's 6 to 8. There's also the in-lab midterm, which is also on Monday, but it's just during your lab time. So instead of having like a normal lab, it's just going to be like an in-lab exam. So that means that you'll use Snap and you'll like code up. Usually it's a fractal, so that's why we're kind of focusing on fractals. So yeah, that's the in-lab midterm. And then last thing is instructor office hours. I have instructor office hours tomorrow from 12 to 1 on Zoom. I still need to link the link in the Google Calendar, but I'll do that after class today. So please come to those if you have any conceptual questions or logistical questions, or you want like study tips for the midterm, anything like that. Feel free to stop by those. Those are going to be at 12 tomorrow. And then Maddie has instructor office hours at 10 on Friday. And I think hers are also online. But yeah, if you guys are interested in us having like instructor office hours in person, maybe like make a post on Ed or like send us an email and we'll like see if we can set that up. But yeah, are there any questions about any logistics, like midterm or anything else? Good. Okay, great. Also, I forgot to ask, but can everyone, like, is the screen okay? Like for people in the back, is everything visible? Okay, awesome. Okay, let's go ahead and get started with content then. So yeah, as I said, we're going to talk about fractals today. How are you guys feeling about fractals? Like thumbs up, side, down? Okay, I see like pretty much in the middle. So that's good. That's a good place to be. I'm going to go through like hopefully 4 examples at least. We're going to walk through like kind of a general process for approaching them and also like build a little bit more intuition about it. I think a lot of this might be review from your lab. Have people mostly finished the lab of fractals? Yes. Okay, cool. Yeah. So I think the first half of this might be a little bit of a review, but I think that it's helpful to kind of walk through it to build intuition for why we're doing this stuff or like why it works the way it does. And then we'll go into like some more examples. So yeah, so just broad definition of fractals. Fractals are a visual application of recursion. So basically a fractal can be defined as an infinitely complex mathematical shape. Basically, it's just a recursive pattern. So it's like some sort of pattern that keeps on repeating itself. Maybe it keeps getting smaller and like you have more and more of the pattern put together. And fractals are really commonly seen in nature. And that's kind of how they were like discovered as a concept, is they're actually like super visible in nature. So I think snowflakes are probably like the most like easiest example to see like that is kind of like a fractal. But yeah, snowflakes, lightning, tree branches, leaves, all of these things are things in nature that naturally just have a recursive pattern built into them. And that's really cool because it's actually like a really complex like mathematical concept, a fractal, but it just exists naturally in nature. So that's really cool. And so what we're going to do in CS10 is we can create drawings of fractals in Snap. And we do this using command blocks that take in like an input of like a size and a level number. So yeah, that's what we're going to be doing with it. And usually this appears on the in-lab portion of the midterm. It says more info to come on this soon. Basically, the information is already out on the logistics post. But yeah, that's just an intro to fractals. So what we're going to do is we're going to first start out with trying to build a fractal from scratch. So we're going to discuss how we can build a fractal from an initially blank program. Our goal is going to be to generate a section of the coach snowflake. And so this is what I was saying, sorry, that I think you already did in lab, but we're just going to kind of walk through it again. So first, we're going to kind of discuss this conceptual idea behind the fractal that we want to build. So we're going to kind of start out with is the coach snowflake familiar to you guys? Do you guys remember seeing this in lab? A little bit? Okay, cool. Yeah. So we start out with the line. So this is basically our level 1. Okay, we start out with our line, level 1. And then at depth 2, instead of having 1 line, we actually have 4 lines, and they're kind of like tilted around a little bit to form this little like triangle shape with 2 lines on the side, basically. And something that's important to notice is that this level 2 fractal, our line is 1/3 the length of the original level 1 fractal. And we also have like a 60-degree angle here. So now if we look at depth 3, it's going to be the same thing, except now we're going to take our level 2 fractal and we repeat it 4 times, and we match these same angles that we did from level 1 to level 2. We do the same thing from level 2 to level 3, except we're using the level 2 and making copies of that instead of making copies of level 1, which level 1 was just a line. Does everyone see like how this pattern is just repeating itself between these 3 levels? And so if we keep going, we can see level 4 looks like this. So now we have our level 3 fractal, and we have this, and it's going to be like turned, rotated, and repeated this way, and then repeated this way, and then repeated across again. And so once you basically know these 2 levels, you can technically draw any level of fractal if you like think about it enough, but it's really complex to like do it by hand, obviously. So that's why we have computers, and that's why we're going to write it in Snap. But yeah, I think there's maybe one more level. Yeah, this is level 5. So it'll be using this level 4 fractal and just repeating the same thing over and over again. So the different colors correlate to one recursive piece of the previous level. Does this make sense how each one translates to the next level? Okay, I'm gonna keep going then. So yeah, now we can talk about like our approach for how we're gonna code this. So again, you might have seen this in lab, but first we're gonna hard code our depth 1, depth 2, depth 3, and kind of see if we can observe some sort of pattern that'll help us write a recursive solution. So this is like our level 1, level 2, level 3 fractal down here, just to visualize it. So for level 1, if we just want to make our snowflake our level 1, all we have to do is make a line, right? So in our code, we can just write move size steps. Remember, we said that our input is going to be the size and our input is also going to be the level. In this case, we don't need a level for our input right now because we're hard coding each of the levels. Depth is also just referring to a level. Yeah, so flake 1 is just making our level 1 fractal and it's going to move size steps. And now if we want to do level 2, which is like our flake 2 fractal, we're going to it's going to be a little bit more complicated. I mean, we already have a lot more blocks than just in flake 1, but we're going to move size divided by 3 steps. So if you remember at the beginning, I mentioned that the lines are 1/3 of the previous size. So we're going to move size divided by 3 steps, and then we're going to turn 60 degrees counterclockwise so that we can face this way and kind of move up this line. And then we're going to turn again so that we can move down this line, and then turn again, and then move straight across, right? So that's the rotating and stuff is just the way that your sprite's moving. So does everyone see like how flake 2 is drawing this picture? Yeah, okay. So something to notice here is that this block right here, our move size divided by 3 steps, is exactly the same as our depth 1 snowflake segment, right? And we already know that because we already talked about, just looking at this picture, how this picture is being repeated 4 times, right? And we defined our flake 1 block to just be moving size steps, and size is an input. So the only difference between this line of code and this line right here is the number of steps that we're moving, but that's just a variable, so we can just pass it in as size divided by 3. So we could replace this block. Can you guys see my cursor well enough, what I'm pointing to? It's like this block, this block, this block, and this block. All of the move blocks can be replaced by a flake 1 with size divided by 3. Does that make sense? Okay, so I don't think I have a slide showing that exactly, but if we try to draw the flake 3, we can basically do the same thing, because again, we're just going to repeat this picture 4 times. And between each of those, we're going to rotate appropriately so things are tilted the way that we wanted it to in our picture. And we can just use our flake 2 block instead of doing this every time. Because if we did this every time, like our code would get super, super long, right? If we had to make each of these 4 lines individually the way we did it here to make each of the 4 lines, it would have to replace each of these purple blocks with like all 8 of these blocks. And that would make our code really, really long. And we want to keep our code simple. So that's why eventually we're going to make it even simpler than this, but we're going to move to recursion to do this. But this is how we're kind of like noticing this repeated pattern that we already noticed visually, but this is what it kind of looks like if we were to code it. Does that make sense? Okay, so ultimately the conclusion that we've drawn from these first 3 levels that we're looking at is that if we have access, aside from level 1, so level 1 is kind of like our base case, which we'll see in a second. But aside from level 1, for any other level, if we have access to kind of like a helper block, you can think of it like, if we have access to a helper block, which will do a specific level of the, if we have access to a helper block that will do the previous level of our fractal with an input size, then we'll be able to draw the current level of our fractal, right? So for flake 3, for level 3, we had to have access to our level 2 block, and we have access to this level 2 block. Now, if we wanted to draw a level 4, we could do flake 4 size, and it would look very similar to this, except this would just be the flake 3 block for all of these flake 2 instead, because we're trying to draw level 4, right? So as long as we have access to a helper block of the previous size, then we can draw a fractal. Does that make sense? And so the way that we do this with recursion, and I'm going to walk through like a different example, but I just put it up here because I think you guys did it in lab. But the way that you would do this recursively is you can kind of have your if statement. This is for our base case. If n equals 1, so that's the level. If we're at level 1 or depth 1, we're just going to move size steps the way that we did it here. Otherwise, we're just going to have like a purple, blue pattern going, because our purple block is referring to our recursive call to the previous level. So basically, this kind of functions, you can think of it as having a helper block that completes the previous level of your fractal. And this goes back to like the fundamentals of recursion, because remember when we started talking about recursion last week, like we talked about how recursion involves calling the block that you're defining within the block definition itself, right? That's like ultimately what the definition of recursion is. And we kept telling you, we kept repeating this, that you need to kind of like take the recursive leap of faith and assume that this block works without implementing it fully. And that's exactly what we're doing here as well. Like we're assuming that we can do a level n-1 and a size divided by 3. And we're assuming that that's going to work because it's a smaller level. And if we can make a call to a smaller level, then we know that we can draw the current picture, because in this example, for every single snowflake that, or like every single level of our snowflake fractal that we want to draw, we just need 4 of the previous levels, and then we can rotate them as accordingly to make our picture. Does this make sense, kind of like overall how we get this code? Yeah. Yeah, good question. Yeah, so the question was, can I explain why it's n-1? Yeah, so the reason that it's n-1 is because n-1 is basically, so n is referring to the current level. So that's the fractal level that we want to draw right now, or the depth level. And so the way that fractals work is they use instances of the previous level in the current level. So our first level is just a line. So you see in level 2, we have 4 lines. We have 4 copies of level 1, essentially, because level 1 was just this line. In our level 3, we have 4 copies of our level 2, right? And if I just go back really quickly for a second to this side, in our level 4, we have 4 copies of level 3, right? So basically, it's going to just be the previous level. And this is where we're like assuming that our recursive block already works, because we passed in n-1, and that's actually what we need. We need the previous level. And so n-1 gives us that previous level. Does that answer your question? Okay, awesome. Anything else? Okay, cool. Okay, yeah.
I was wondering why are you using in the base case, why are you moving size steps, not size by 3?
Yeah, good question. So the question was, why are we moving size steps instead of size divided by 3 in the base case? And so the reason for that is because ultimately we want to make like a fractal of this size, whatever the size variable is given. But when so that's like the total size that we want to make. If we want to make a like level 2 fractal, for example, then basically like when we pass in size divided by 3 in for the input here, and if n was 2 in this case, we were drawing this one. Then when we get to this level, if this was size divided by 3, then it would basically start making lines that are like 1/9 of the size, because it would divide by 3 twice. But we're providing the input of size divided by 3 for the size variable to like the previous case. Does that make sense? Okay, awesome. Anything else? Okay, cool. Okay, sorry. Let's keep going. So yeah, so this is just like a quick slide about like the background of a coach snowflake. So basically it's called a coach snowflake because I don't know if I'm pronouncing it correctly actually, but I think it's a coach snowflake because we have 3 copies. If you put them together, it'll resemble a snowflake. So it looks kind of like this. Hopefully you saw this in lab already. But yeah, there's like some fun mathematical facts here. Like if the area of the shape is always finite, but as recursion depth increases, then the perimeter is also gonna like go to infinity. So that's like kind of interesting to think about. So yeah, there's some other facts. You can read this if you want in your own time. But yeah, so you did this in lab. Are there any questions about the coach snowflake before we move on to the next example? Are you guys good? Okay, awesome. Okay, we're gonna move on to the C curve now. This is another one that you saw in lab. I don't know if this one was a required one in lab, so I don't know if everyone did it. But this is also an important example, and then we'll do 2 other examples that aren't from lab. So another similar construction, a similar fractal, is called the C curve. And as before, we're starting off with a straight line. So our straight line is our level 1. And then we're going to replace the straight line when we want to draw level 2. We're going to make our level 1, but we're going to kind of like tilt it like kind of 45 degrees to go downwards, and then do the other one like upwards. So basically it's forming a 90-degree angle. So does everyone see how, if this is our level 1 and this one is our level 2, does everyone see how the level 1 can kind of translate into the level 2? If we have 2 copies of level 1, we just kind of tilt them in a specific direction in order to make this. Does that make sense how there's two of these in this? I know this might be kind of basic, but I want to make sure. Okay, so now how can we draw the next step? So the next step or the next level, I know there's lots of words referring to the same thing, but this is our level 1, this is our level 2. Can anyone tell me what the level 3 would look like for this? Any ideas? You can just kind of like describe it. Yeah, I see some pictures being drawn in the air. So basically what we need to do is we need to take our level 2, we need to rotate it. So if our level 2 currently is like this, we need to rotate it basically 45 degrees because we had our level 1 that kind of looks like this line. We rotated it 45 degrees to make one side of the line and then 45 degrees to make the other side of the line, right? And so now this is our original starting point. I know this isn't, I should probably draw it. This is our starting point. If we have like this is not 90 degrees, but pretend this is 90 degrees. We want to rotate this 45 degrees this way. So it's actually going to become like this. Can you guys see this in the back? Okay. And so it's going to rotate and this way, and then we'll try a different color on this side. This is the other one. So this was our level 1, used twice, and now this level 2 is used twice in our level 3. Does that make sense? So it's kind of just going to look like a half of, or the 4 sides of the rectangle. It's not, yeah, it's basically this picture right here. I was just trying to draw it out. So it's like this angle, but it's rotated 45 degrees. So pretend there's like a split here, kind of. That's where like the 2 sides that come from. Does that make sense? I can also draw it out again, maybe with the 2 colors. Would that help? Yeah. So okay. Let me do this again. Okay. Let's try it over. I don't know. This will be better. So this is our level 1, right? Is this line? Can everyone see this line? Okay. And then our level 2 is gonna be this, but rotated 45 degrees. So this way. And then it's gonna be our other level 1 inside of our level 2 is gonna also rotate, but it's gonna be like a reflection of it. And pretend this is 90 degrees in the middle. This is our level 2. Does that make sense? And so the way that we got from level 1 to level 2 was we rotated our level 1 45 degrees, and then we rotated it 45 degrees in the other direction and connected them at the bottom. So what we're going to do for level 3 is we're going to do the same thing. We're going to take this level 2 picture. Yeah.
Wait, so is the first line the same length as 1/2 of the second one, or is the second one the first line split in half?
Yeah, so
like,
this
is
would
it like this and then this, or is it like just this and then it adds another one?
yeah, good question. It is, so our fractals always are going to be like what a fraction of the previous size. So in this case, it's like basically 1/2 because it takes up the same amount of space as the level 1. Because the thing is, ultimately, every fractal of the same size should take up the same amount of space overall. So this is 1/2 of this, and this is something that you don't necessarily need to like figure out. When you're given a fractal problem, it'll tell you like each line is 1/2 the size of the previous level. So that'll be something that's given to you. But yeah, whenever you're making a recursive call, whatever the instance of the previous level is, it's always going to be smaller, because otherwise your fractals would get like infinitely large. Does that make sense? Okay, yeah. So sorry. And then continuing on with this. So now we wanted to rotate this angle like this, 45 degrees. So this is one rotated 45 degrees. Now our right angle kind of looks like this. And then if we did another copy of this, but rotated 45 degrees this way, it would look something like this. Does that make sense how we got from level 2 to level 3 now? Are there any questions about that? Okay, yeah.
So it's like we take the last one, we rotate it 45 degrees, and then we just mirror it, right? Like
Yeah.
flip it on the other side.
Yeah.
Okay.
Yeah. It's basically like a reflection like over the y-axis, I guess,
Yeah.
on the other side. Yeah. Anything else? Yes.
So then the next level, it would just rotate it another 45 degrees as well as add another 4.
Yeah, exactly. It's going to rotate it again. So I think there's, yeah. So now our challenge is drawing step 4. So basically, I'm just going to put it up because it's kind of hard to describe. But in the future, you should try these out and see if you can draw them out. But it's going to look something like this. So this block got rotated 45 degrees, kind of on this way, and then it got rotated 45 degrees the other direction, and like this. And we see that it's symmetrical again, because it's kind of like we're being reflected over the y-axis. Does this make sense? Okay, so does it make sense how we got like through the different levels? Okay, cool. Let's keep going then. So yeah, in lab, you're gonna implement this fractal, or maybe you already did this. But yeah, that was just an intro of like what this is. Yes. The angles. Like if it was turned a different amount. Or sorry, what were you? Oh, yeah. So this is basically like this. This is 90 degrees. So if you imagine there's like a line here, then this is going to be 45, like this, and this is also going to be 45. And then these are 90 degrees because these are just this angle rotated. Does that make sense? Sorry, I don't know if this is clear. Maybe I can. Yeah, I mean, yeah, basic. And then the other thing about fractals, like the angles aren't going to be like super like weird. Like you're not going to like be like, basically you can, it should be kind of what it looks like. So this kind of looks like a right angle, right? Like this angle here, and this one kind of looks like a right angle. Whatever it looks like is what it is. We're not going to be like, oh, this is actually 85 degrees. It's not 90 degrees. It's just kind of what it looks like in like the problems that you're going to be given. So yeah, it'll be clear what angle it is. Yeah, sorry, did that help? Is this what you wanted? Okay, yeah, let me know if you want more clarification on that. But yeah, are there any other questions about this example? Okay, cool. Okay, I'm gonna keep going. I think, yeah, so now I'm gonna talk about an approach for coding fractals. I think I don't have the solution for the C curve on this because you do it in lab. But yeah, just wanted to go over how we can visualize those pictures. So now we'll actually code a couple solutions to other fractals. But before we do that, I wanted to just go over kind of a general process for approaching fractal problems. So this isn't like an actual like process that's defined anywhere. This is kind of just like what we as CS10 staff over the years have kind of developed as like a good technique for following through. So this is like a bunch of steps, and this is what I recommend doing. So I think kind of if you can get this down, you can kind of apply it almost as a formula. Obviously, every fractal is different, so it's not going to be exactly the same. But if you kind of understand this process, you can apply to any fractal, and once you master that, you'll be able to do any fractal. So the first step is to identify the instances of the previous level in the current level to get an idea of the overall pattern. So that's kind of what we were just doing with the C curve. We want to identify the instances of the previous level in the current level. So if this is our current level, this is level 2 is our current level. Our previous level we know is just a line. So we want to identify which instances in this current level are the previous level. And in our example so far, every line or every like thing in our fractal was part of a recursive call, was part of a previous instance. But sometimes there might be something that's just always exists in every, like for example, with the C curve, say that every instance other than the base case had like this line here or something, but this line doesn't get changed. Like we know from here to here, everything's just a line. But then when we got here, our previous level, it wasn't a line anymore. It was this like L shape. But if this doesn't turn into an L shape, then that means that this is not part of a recursive call, because that means that we only have 2 instances of the previous level. We just have this one and we have this one, right? But this one is not an instance of the previous level. This is just an extra line that exists, and that's okay. Everything doesn't have to be part of a previous level, and there's an example of that right after this slide. But this is an example where like the line might not be part of a previous level. So the first step you want to do is identify which ones those are. And usually if it's not obvious, we will usually bold these lines to kind of show you like, okay, this is the instance of the previous level. And if it's not bolded for whatever reason, I recommend that you kind of like highlight that or like circle that, just so that you can see it. Like if you see it on a midterm, maybe circle the instances of the previous level, like the way I did right here, just so you can visualize that, and you'll recognize like how many recursive calls you have to do in the code. So that's the first step. Next thing is create a command block that can take in a size and level as input. Basically, this is just setting up your snap. So just create a block that takes in a size and a level that draws your fractal. And then the third step is we want to code the base case. So if you remember with recursion in general, not even talking about fractals, the base case is always your level, your simplest instance, basically, right? So in fractals, what is going to be our simplest case? What's going to represent our base case? Which level? 1, right, exactly. So we're going to add an if-else block into our block definition, and we're going to use the n=1 drawing to draw the base case using move and rotate blocks. Or like, I think it's called turn, not rotate. But yeah, so we basically are going to just look at our level n=1 picture. So usually when we give you fractal problems, you'll probably see like at least 4 levels of the fractal to get an idea, but just don't look at anything else for the base case. Only look at level level n=1 and just draw out what that needs to be. Sometimes it's really simple. It's just like a line. Sometimes it's like a little different, but just explicitly draw out whatever's there. Then something really, really important is you want to make sure that the sprite ends facing the correct direction. So this is another thing that will be visible on your fractal like problem. Whenever we give you a fractal problem, we'll show you like, you'll see the sprite on the problem. And when you see the sprite, then you'll kind of be able to tell which direction it's pointing. You want to make sure that at the end of your base case, the sprite is pointing in the direction that's pointing in the picture that you were given. So that's really important because since recursion is like using the other code to kind of turn and stuff, like if it's not pointing in the correct direction, your fractal, like maybe your level 2 instead of like looking like this, or sorry, your level 3 instead of looking this, it's going to be kind of turned because the sprite, if it ended up pointing up instead of pointing to the side or something. So you want to make sure that your sprite points in the correct direction. Does that make sense? And maybe you already saw that in lab. But yeah, last step, we're going to code up the recursive case. So what I recommend is try to code the recursive case, which is going to be in your else case, right? We try to do this by just looking at level n=2 to start with. If you try to look at all the levels, sometimes it gets really overwhelming. Like, oh, like this fractal looks like really complicated. Even just looking at level 4 sometimes looks really complicated. But something about fractals and recursion is like only the base case is like explicitly defined. Everything other than the base case is actually the same exact case, right? And we saw that because, okay, like level 1, our base case was just a line. The level 2 was just the level 1, but rotated 45 degrees and made 2 copies. Level 3 was just level 2, rotated 45 degrees, and 2 copies of it were made. So every other case is the same. So just look at level n=2 because that'll just make your lives easier. Just look in the n=2 picture and draw all the non-bolded lines. And so by bolded, maybe you like noticed which ones were the recursive pieces. Draw those lines normally with like the move and rotate the way that you normally code it. And then you want to make a recursive call to the previous level with the appropriate size. And again, I said that we'll tell you like the size if it's not obvious, if it's like half the size or a third of the size, but make sure you reduce the size appropriately. And you also make a call to the previous level whenever there's like a bolded or highlighted line. And the bolded highlighted line just means like from this first step, when I said identify the instances of the previous level in the current level. Does that make sense? And basically that's it. Those are all the steps. And then again, you want to make sure that your sprite ends up pointing in the correct direction. So this approach, you can do this for any fractal. You can basically code any fractal by just looking at n=1 and n=2 if you have all the information about like which are the recursive parts. Sometimes it's hard to tell which are the recursive parts by only looking at level n=1 and n=2. So that's why we want to, in this first step, you can look at everything to see like, okay, where are the patterns repeating? Like if I talked about this line over here, this line is not a recursive piece of this because it doesn't change. It's just a straight line every single time. But these lines are part of the recursion. So that's how we would kind of identify the differences. Does that make sense? And again, usually this will be bolded if it's not obvious. But that's why I think that first step is really important. Like make sure you know what's going on. Make sure you know where the recursion is happening. Does that make sense? Are there any questions about this? Okay, yeah, the slides are posted. I think earlier, like people didn't have access, so I think I fixed that. Let me know if you still can't access the slides, but I think this is a good like method to use personally to like do fractal problems. So yeah, oh sorry. And then the last step is just check the n=3, n=4. So and this is important, is like, okay, after you do this, I said you only need to look at n=1 and n=2 technically to code it, assuming that you recognize where the recursive pieces are appropriately or accurately. But you still want to check n=3 and n=4 as well, just to make sure that everything is working correctly. Because usually you're given all 4 pictures, all 4 levels. So you want to check all of them to make sure that it's correct. that make sense? Okay, are there any questions about this? Are we good? Okay. We're doing okay. I think we'll get through at least one example, maybe another one. But yeah. Okay, so this is what an example problem looks like. This is just like describing what it'll look like when you're given a problem. Basically, you're going to be given a picture of the first few levels. This is our n equals 1, n equals 2, n equals 3, n equals 4. You should see how each level contains instances of the previous level. So it's kind of forming a pattern. Typically, the instances of the previous level are going to be bolded. And your job is going to be to code a command block that can draw any level of the fractal given some level and a size. And again, we're going to tell you the size of the repeated instances relative to the previous level. And if you look at this example that we're about to code, it actually looks very similar to the Coach Snowflake, but it's actually not the Coach Snowflake because, and this goes back to recognizing where your instances of the previous level are. But does anyone see why this is a little different from the Coach Snowflake? Yeah.
You only added another like bend on the
Yeah, like on this one, right? This is what you're talking about? Or like this?
yeah.
Yeah, so,
Any other one, like does it only on continue to the right?
yeah, yes, yeah, exactly. And this one as well. So yeah, and if we talk about like the bolded lines, like only 3 of them are bolded. I know I didn't show a picture that had the bolded lines before. But yeah, basically the idea is that there's only 3 instances of the previous level in this fractal. Whereas with our Coach Snowflake, we had 4 instances. All 4 of these lines were part of level 1. So this is an example of how you kind of need a couple levels to see where the instances are if we don't bold them for you. But now if we look at from level 2 to level 3, it's clear that there's only 3 instances because level 2 is this little like spiky thing. There's only 3 of those spiky things. There's not 4. If this was the normal Coach Snowflake, then this one would also have the little spike here, but it doesn't. So that tells us that we only should be making 3 recursive calls, not 4 recursive calls like in our other version of this. Does that make sense? Okay. So yeah, we're gonna go ahead and try to code this now. So this is the same thing as the previous slide. We have our level 1, level 2, level 3, level 4. So kind of the first thing that I said that we want to do is we want to so we first want to identify the instances of the previous level in the current level. So I kind of already talked about this. In this case, the lines were bolded. So, but just to see if you guys remember, how many instances of the previous level are in each of these for the current level? So 1, 2, 3, 4. What do you guys think? Or how many lines are bolded in even just looking at level 2? 3, right? Thank you. So we have 3 instances. It's this line, this line, this line, and just to make sure we can look at the future levels and see, again, like I just mentioned, we have 3 of these little spiky things. Okay, so that makes sense. There's 3 instances. Just double check with the 4. We have 4 instances of this little star pattern. 1, 2, not 4. We have 3 instances of the star pattern in level 4. So we have 1 here, and 1 here. So that tells us we have 3 instances in the current level of the previous level. So we're going to have to make 3 recursive calls in our code. Is that clear? So, okay. So moving on. So we make this block definition. We have it taken a size. We have it taken a level n. And now we're going to first code the base case, right? And which picture are we going to look at for the base case? Exactly. Thank you. N equals 1. So we're going to look at n equals 1. This like arrow thing here is kind of just to show you how I recommend just kind of like thinking about when you're drawing it. So imagine you have like a little pointer, a little pencil, and when you're writing the code, you just want to do exactly what you would have to, the directions that you would have to give to someone with a pencil for what they would have to do. So starting here, we're just going to draw. We're going to just draw simple lines. So what block do we use to just draw one line? Move, exactly, right? So we're going to move from here to here. That's what we need to do. So if n equals 1, that's our base case. We're going to just move size steps, right? Does that one make sense? Okay, great. So moving on, now we're going to do the else case. Which level did I say we should look at to code the else case? Yes, yeah, thank you. Yeah, n equals 2. So we're going to look at the n equals 2 level. Again, the else case applies to any case that's not n equals 1. But you can just look at n equals 2 and go from there and then see if the other ones work as well, because all of them are going to be following the same pattern. So again, we have a little pointer here. So the way that we draw the else case, or the n equals 2 case, the first thing we would have to do is make a line. So how would we make a line? We need to go from here to this point. What are we going to do in our code? We're going to move again, and we're going to move size divided by 3 steps. So like I said in the problem, it'll tell you, in this case, it's 1/3 of the size of the previous instance. So we're going to move size divided by 3 steps, right? Now, what's the next thing we need to do? So we're here, we made our line like this. Now we need to make this diagonal line here. So in order to make that diagonal line, we have to turn like this, right? So our little pointer is going to turn like this. And how many degrees does this look like it's going to be? 120, is that what you said? Yeah, so this is kind of weird. I think it's actually 60. It's like, you have to imagine, that's why I use this little pointer. Like, you imagine that you're like this, and then you're rotating like this. So it's kind of like this angle is 120, but this angle that you have to turn your pen is 60. Does that make sense? So yeah, that can get really confusing. So it's important to kind of like visualize it. So yeah, we're going to turn 60 degrees this way so that we're ready to make our line. What are we going to do to make our line now? Yeah, so we could move, but remember this one is bolded. So since our line is bolded, what do we have to do? Yeah, yes, exactly. So we're going to make a recursive call. What is our recursive call going to look like? Yes. Yep. Yeah, exactly. Thank you. Yeah, so we're going to draw a fractal of size divided by 3. So we want to reduce our size, but it's not just going to be -1. We want to do it like relative. So it's going to be like a fractional size. So it's going to be size divided by 3, and it'll be level n-1 because we want to just do the previous level, which in this case was just the line. So great. So now we're here. We moved from here to here. We made this line. Now what do we have to do? We have to change from this. We want to be looking like this. So how many degrees? Oh, I already put it up. Okay, so from here, we have to go here. We're going to turn 120 degrees. So we were like this. We turned 60 degrees to be like this and go like this. Now we want to turn like this. So we want to overcompensate for what we did before. So not just turn 60 degrees back to be this way. We want to turn 60 more degrees to be this way so that we can go down and make this angle right here. So we're going to turn 120 degrees. And now we're going to move from here to here. So what are we going to do that? Yep, we're going to do recursion again. So we're going to make another line using our recursion, and we're going to make the exact same call of size divided by 3, level n-1, and now we've ended up here. And we're going to do the recursion here because the line was bolded, so we know that it's the previous one. Does that make sense? And so now what are we going to do? Now we're pointing like this. What do we have to do next? We have to turn back so that we become flat again, right? So this is going to be turn 60 degrees, and then what's our last step? Yeah, a recurse again. So we're going to do the same exact thing, just make a recursive thing. And we see our little like pointer thing that we're imagining ended up pointing in this direction, which is good. We saw that our sprite here is supposed to face this way. It's really small in the slide, but you'll be able to see it better when you actually have the printout. But yeah, we ended up facing the right direction. So this should be good. And all we looked at was level 1 and level 2 to actually write the code, right? But this is going to work for everything else as well. And you would see that if you tested it out. Does anyone have questions about this example? So again, the key thing here that makes it different from the code snowflake is that this line here is not made by a recursive call. So that was like the kind of like the random line that I drew here. It's not made by the recursive call. So now when we do level 3, it's just going to move. So every time it'll just be a line. Whereas in these cases for level 2, it was just a line on this purple block, but it's not always going to just be a line. It might just be the actual previous instance. Does that make sense? Okay, any questions about this? Okay, cool. I think we're kind of running low on time, but maybe I can just start going through. Okay, maybe we can just talk through this a little bit. So I was going to code it in Snap, but I don't think we have time today. But basically the way that you would approach this is you first want to find the previous instances, right? So how many instances of the previous level are in each of the current levels? Can anyone look at this? Take a second, take a look at it, and raise your hand if you think you know the answer. Yeah, exactly. There's two. And we can see that because we see that level 1 is just a line. We see 2 bolded lines in our level 2 instance. And just to confirm, we see this is our little shape that we want to make. And we see that shape here. It's kind of harder to see on this, but we see one of those shapes here and one of those shapes here. And this one's even harder to see, but we can kind of like see this image is like kind of here and also here. So that tells us we maybe want to make 2 recursive calls. So in our base case, it's going to be really simple. Again, we're just going to make a line all the way across. Whereas here, we're going to want to start at this point, and you're going to want to first rotate maybe 60 degrees, and we want to make this line, and then we want to rotate back 60 degrees, make a straight line. So both of these are just going to be moved. And then once we get here, we're going to start doing recursion because we have these bolded lines. So we're going to make a recursive call to the previous level and a smaller size, probably size divided by 3 again, to go down here, rotate and make another recursive call and ensure that we're facing the correct direction at the end. That makes sense? That would be kind of how you do this. I don't really have time to go over it right now, but this is actually like a previous exam problem. Like I think it might have been my fractal when I took this class. So yeah, this is like very much the level of what you will be seeing on your exam as well. Really quickly before we go, I'm just gonna go over these like tips that I had, reminders. This is basically everything I've said, but just kind of summarized again. I just want to reiterate. So first and foremost, you really want to make sure that your sprite is ending up facing the direction that it started in both cases, both in the base case and the recursive case. It might be pretty often in the base case that you don't need to turn at all, in which case it's fine. But if you do any rotation, you want to make sure that it ends up facing the same direction that it started and also like the correct direction. And so if like just a little tip for that is if you're turning like clockwise and counterclockwise a bunch of times within your code, add up all of the clockwise turning and add up all of the counterclockwise turning. And if they're equal to each other, then that indicates to you that your sprite ended up facing the same direction that it started, which is usually what you want. If they don't add up to the same amount, then your sprite's going to end up tilted some direction. So you want to make sure that they're adding up to the same amount. Next thing is try to just look at the first couple of cases when writing your code. Don't get overwhelmed by those higher levels. So like I said, if you know where your recursive pieces are, you only need levels 1 and 2. You don't need those future levels. You can just look at 1 and 2, code up your fractal, and then try out the future levels and make sure that they work. Yeah, remember to decrease your input. So both size and level need to be decreased. So size is decreased by some factor, which is usually given to you. And then level is always going to be level -1 because you're just making a call to the previous instance of your fractal. And then also you want to make sure that you're only calling your recursive function if the line is part of a previous instance, not just if the shape looks the same. So that's what I was talking about. Just because it's a line and the level 1 is also a line, that doesn't mean that you want to make a recursive call. You only want to make a recursive call if it's actually supposed to be a previous instance. So if it's bolded, basically. And then lastly, I just want to say that sometimes it can be useful to have some sort of like setup code for going to a starting position, clearing the screen for testing purposes. Maybe you've like kind of noticed this in lab, but if you keep testing out your fractal, it can be really annoying to like make your sprite go back to its like starting location, like clear the whole screen, like, okay, and then you move your sprite and then it draws on the screen again because your pen was down and then you have to clear it again. So you want to kind of just have some setup code to begin with. That's just like a tip that I have. That way, when you're working on your like in-lab midterm or something, if you have that code already written, then you can just code up your fractal and keep clicking that and it'll like clear your screen and everything. But yeah, that is, I think, everything that I have. I think this was the last slide. But yeah, that is everything I have today. Thank you guys so much for coming. Hopefully you guys got a better understanding of fractals and make sure to go to discussion today. We will see you tomorrow. Thank you. Yeah, one second.